All right. Normally, when I pick my classes for the semester, because of the recording stuff I do, I try and make it so that my classes are close to each other, or I give myself enough time between classes to get to my next class. Does that make sense? Like I don't do back-to-back classes unless I'm in the same classroom. But because I had to pick up that class for that faculty that passed away, I'm having to come all the way from LOH, third floor, with all this crap with me. And so I think I'll probably be about a minute or two before I'm completely set up from here on out. So my apologies, but it's kind of the situation I'm in now. So just wanted to address that. Also, Chapter 11, Section 8 notes. I did get several emails that the file was not opening. So I went ahead and I redid the file where I just took out all the pictures, because that's really what makes it such a large file. So all the pictures are gone. So the only thing you really have to look at today is what I do in class with the video. But you'll still see all the notes and all the formula, or yeah, all the techniques and stuff that we're going to be using. And all the examples are there. Did you get that, Allie? Yes? Okay. How are y'all doing? We have a test coming up. As I was walking into class, on campus today, I was thinking about, Monday's test and everything. So let's talk about the end of class, see where we are, see how we feel. I've been considering possibly moving it till Wednesday, but I don't know. I want to see what you all feel about that. The drawback would be we would have 11.8 would be on it also. So let's start looking at 11.8 and then we go from there. All right. So 11.8, Lagrange multipliers. So here's what we've learned so far. We can find the local max, local minimums, and saddle points of a function on its implied domain. So if you don't restrict the domain of a surface, we can find where they have high and low points and then saddles. We can do that. We do that by calculating that capital D, right? And then last class, we said, well, if you take this surface and you restrict it to a closed bounded set, then we can still find max and mins, but now we can find absolute max and mins, and the process is a little different. We still find critical points, but then we have to go around the boundary and find out, what's happening around that edge. But we should be able to handle both of those cases. We now develop a very, very powerful method for finding the maximum minimum values of a function subject to a constraint. In other words, we are going to take a surface, and we're going to see that it doesn't even have to be a surface. It could be in higher dimensions. But we're going to take a function, and we're going to restrict it again. I mean, we restricted the domain right here. But this sort of restriction is going to be a little bit different, as you'll see. And if we do that, we're going to be able to find the max and mins. So here's the method of Lagrange. Lagrange is a mathematician who gets credit for this method. Here's the method when you have two variables. So if we have a function, f of xy, subject to a constraint, g of xy equals k, then we do the following to find the maximum minimum values. We find all the values, x, y, and then we're going to use this lambda, such that this is true and this is true. Now let's look at, what does that first one mean? What is this saying? The gradient vector of the f function, right? The f function is the thing we're trying to find the max and min of. We want to figure out when the gradient vector of the f function is equal to lambda times the gradient of the g function. Now the g function is our constraint. And we also, at the same time we find the x, y, and lambdas that make that true, we are going to also make sure that the x and y make the original constraint equation true. All right, now geometrically, remember we said the gradient is a vector? Yes? And here, this is a vector. The gradient of g is a vector. Multiplying a vector times a number means it's a scalar multiple, which means that we're trying to figure out where the gradient of f is parallel to the gradient of g. If we figure out where that happens, then we will have found where the maximums and minimums occur. Once we find the x, y, and lambda that make these two things true, we evaluate our original function at the points x and y from this part, and the largest is our max, the smallest is our min. Now, for a long time, I taught this Lagrange method, and I didn't really give any sort of like why it works, okay? But last semester, I spent some time putting together something to kind of explain why. So let's see how this goes. We'll do the problems and stuff in a minute, but let me show you why. Try and give you a geometric explanation as to why the Lagrange method works. So I had to create this thing, and it was fun, but I hope it kind of helps, all right? First of all, we have f of x, y, right, which is our surface. And we are going to constrain it using this equation, g of x, y equals k. So the first thing I have in this picture is g of x, y. G of x, y is just another surface, okay? G of x, y. Now, if I say, let's let g of x, y be equal to k, then what I'm doing is I'm getting a level curve off of that surface. All right, a level curve. Remember when we were drawing surfaces, we said we could draw the different rings and get an idea of what it looked like, but we don't really do that anymore, or I don't like to do that. But if we were to take this surface and say, when is that surface equal to a constant, it would give us just one level curve on this graph, right? It would give us that one right there. So now what I'm going to do is I'm going to pull the surface G out. Something didn't happen there. Why didn't G come out? Okay, let me try this. G should have gone away when I did that. Okay, let me show you the gradient of G. Oh, there it goes. My computer's thinking, I guess. So I pulled the surface out. There's that level curve, right? And the gradient, remember we said that the gradient vector is going to be, if you look at it from here, the gradient vector in this case is just a vector, right? And it looks like that gradient vector is perpendicular to this tangent line, right? Yes? That's what the gradient looks like. At this particular point, that's what it looks like. Now remember, going back to this, not that. Going back to this, not that. Where the hell is it? My other one disappeared. Well, I'll just write it down over here. What we needed was gradient f to be equal to lambda gradient g, right? That's what we have for Lagrange to work. Wherever this happens, wherever that happens over there, I should be at the max and mins. So that's the gradient of g. Got it? Restricted g equals g at k. Now what I'm going to do, just so it doesn't get in our way, I'm going to drop that ring straight down onto the ground. Because remember, what we're doing is we are taking our f function and we are restricting it to that g being equal to k. So I'm restricting the domain. Instead of looking at f everywhere, I'm saying only look at it where that g was equal to k. So that's basically that ring down on the ground. Okay? Now what I'll do is I will throw the gradient down there on the floor so you can see it, and I'm going to get this thing completely out of here. So I'm just projecting that ring and that gradient down to the ground. All right. Now, Let's bring F into the picture. Here's F. Now F looks like G, but that's just because of what I picked. So there's F, all right? I want to restrict F now to the constraint. So imagine taking just the points on this ring and mapping those up into F. Then you get this blue curve, don't you? Yeah? That's the blue curve is F constrained to that equation G equals K. G of x, y equals K. So I can pull F out now, if that's okay with you. I'm trying to find the highest and lowest points here. Yes? Now let me show you the gradient. Well, where's the gradient? There it is. There's my gradient vector. You see it? Now over here on the right, I didn't really mention this on the right, but the right is us looking straight down. Okay? And so if I look straight down on this thing, do you see that G's gradient's here, right? And here's that blue gradient looking from the top. Now watch what happens as I move around this thing. I'm going to start moving. So I'm moving around this circle, right? And that's giving me a point up on the blue function. And look what happens when I get up to the top of that highest point. What do you notice about the gradient vectors over there? Right there. What happened? They're what? They're parallel. They're scalar multiples of one another, aren't they? And that's what this is saying. Anywhere that the gradient of F is parallel or scalar multiple of the gradient of G, you are going to be at a highest or a lowest point. If I move around a little more, you can see I'm getting close to that lowest point now. Do y'all see that? And as I move around again, those gradient vectors over there, boom, they're parallel. Yes? That's just geometric evidence that it's true. All right? That doesn't really explain why it necessarily works, but that just hopefully convinces you that this is going to work. You with me? All right. Now, I lost that file, so I'm going to close this. I have to close Mathematica. Every time it happens, I have to close the whole program, reopen it. All right, so we're still in the same note. Here's the actual method we're going to use. All right? When we're saying that the gradient of F is equal to lambda times the gradient of G, it means that this vector is equal to this vector. Right? Because remember, gradient was the partials. Which means that if these two vectors are the same, the only way two vectors can be the same is if their components are the same, right? So we match their components up. The first component must equal the first component here. So that gives me this equation, doesn't it? The second component here has to match the second component here, so that gives me a second equation. What are we trying to solve for again? We're trying to figure out the x, the y, and the lambda, right? That make that thing true over there? X, y, and lambda? Right now I have two equations. I have three variables that I'm going to be trying to solve for, right? I have two equations. My third equation comes from the constraint itself. The constraint equation was that G function had to be equal to K. So with these 1, 2, 3 equations and three variables, I should be able to find a unique solution if it exists. So what it's going to equate to is us creating three equations and trying to solve them. Is that a question? Yes. It has to be given. It has to be given in the problem. So going back again, the three things we have are, I can ask you, or anyone can ask you for the local max, local min, and saddle of a function where there's no restriction on domain. That was the first thing we learned. That's calculating capital D. Next thing they could do is lock down the domain to a closed bounded set. That's what we did last class, where you look on the inside a little bit, then you go around the edge, right? Then this method is just the edge. just the edge. Right? That edge, like that circle, was like the edge of a closed bounded set, right? But it's just the edge, not the stuff inside. Does that make sense? Okay, so that has to be given in the problem. I have to tell you what the constraint is. I can't just give you a function and say what's its max and min and not give you the constraint and you use Lagrange. It wouldn't work. All right, here we go. Let's do an example. Find the maximum and minimum values of f of x equals x squared plus 2y squared on x squared plus y squared equals 1. So we have this x squared plus 2y squared is like a paraboloid, right? Like this bowl. If I ask you to find the max and min of this, and I don't give you a restriction, you would wind up calculating d, and you would get the bottom of that bowl as being a local minimum. But that's not what's being asked. You're being asked to find the maximum and minimum of that function on that restriction. Do you see the restriction here? So this right here, x squared plus y squared, is our g of xy, and our equals 1 is our equals k. You see it? And then here's our function f. Now, the picture of what's happening, x squared plus y squared equals 1 is a circle, right? It's actually a cylinder in 3 dimensions, but on the ground it's just that ring down there, right? If I take just that ring and map just that ring up into the surface, I get that curve. Very similar to the problem that I showed where I was trying to convince you what was happening. We're trying to find where those highest and lowest points occur. Lagrange method should let us get those. Is everyone clear, though, that the domain restriction is a curve? Instead of looking at the whole domain or this and everything in it, it's just that edge. All right. So let's actually work it out. The Lagrange is, I dare to say, fun. So we're given f of xy equals x squared plus 2y squared. The constraint equation, x squared plus y squared equals 1. My goal, right, in this whole thing is to find x, y, and lambda such that gradient of f equals lambda gradient of g. That's what I need. I need to find the x, y, and lambda that make that true. Once I find that x, y, and lambda, I look at the x, y's where it happens. That's where the max and mins are going to occur. If they exist, that's where they're going to be. So we said this is going to create 3 equations, right? The 3 equations, equation 1, equation 2, and equation 3. The first equation is the partial of f with respect to x equals lambda partial of g with respect to x. That will always be the case when you're doing Lagrange, where you have a function of 2 variables and you have a constraint like that. You'll always have this as your first equation. Your second equation will be the same thing, but with respect to y instead. And your third equation is just the constraint equation itself. X squared plus y squared equals 1. So this is probably the last time I'll write this down. From now on, I'm just actually going to write what the partial is equals lambda, and then what the partial actually is for that problem. So what is the partial of f with respect to x here? 2x. I want to know when 2x equals lambda times what's the partial of g with respect to x. Now this is a little, I guess, a little tricky. G is actually the left side of this equation, isn't it? G of xy is the left side there only. Follow me? The constraint equation was g equals k. So that side here is g. So when I take the partial of this with respect to x, what do I get? 2x. So come back over here times 2x. Okay, let's move on to the next one. What's the partial of f with respect to y? 4y equals lambda. What's the partial of g with respect to y? 2y. And I don't need to do anything on the last equation because it's just, that's still the equation, right? Now I have the pleasure of trying to figure out the x, the y, and the lambda that make all three of these true at the same time simultaneously. The x, the y, and the z have to make them all, x, y, and lambda have to make them all true at the same time. Well, I see some algebra I can do here. I don't like the 2. I'm going to get rid of that. X equals x lambda. Let's work with that first equation. If x is equal to x lambda, we can try and solve this equation. But remember, don't divide by x, right? What did we do? Brought everything to one side. So I'm working right now. Watch the way I do this. I'm working with the equation 1. With the equation 1, I know that x minus lambda x equals 0. I think in most traditional like Cal 3 classes, at this point, the instructor would just say, and you solve that system and then you get the answer, and that's it. That's the way it was for me. I think it's important to show all the detail here because there's so many little subtleties that you have to be careful with, all right? Let's see. I've moved that over now. Factor an x out, right? I get 1 minus lambda equals 0. So I have two scenarios here, right? I have two different scenarios that could occur. The first scenario is that x could be 0, right? The other scenario is that 1 minus lambda could be 0. I have to consider both scenarios, which means this work is now going to branch off into two new pieces of work. They're going to be their own little worlds. Does that make sense? Their own logical structure for each one. So let me just write down the answers here. X is 0, or go ahead. No. It's just that I have to consider each of these separately. Okay, I started with equation 1. My result from equation 1 is that x has to be 0 or lambda has to be 1. That is the only way equation 1 is true, right? Okay, now, we use this symbol. I'm going to indent this. Okay, so I've indented my work to let you know I'm still working within equation 1. Okay, and I'm still working within this thought process. That's the symbol we use for suppose. It's like a S with a little line at the end of it, the bottom edge. Suppose x is equal to 0. So I'm looking at that first scenario right here. If x is 0, can you get any result from the second equation? If x is 0, x has no effect on that, right? No effect at all. But over here in the third equation, what do you get? Y squared has to then be 1, right? Because that's 0. So I'm going to say, suppose x is 0. That implies from equation 3 that 0 plus y squared is 1, which means y must be what? Plus 1 or minus 1. Well, guess what that means? Now you have to consider those two possibilities. You see that? So I'm going to indent again, and I'm going to say, suppose y is equal to 1. What if y is 1? What can I get here? I can go back to the second equation, right? Y is 1 here would tell me what? 4 equals 2 lambda? So suppose y is 1. That implies from equation 2 that 4 equals lambda times 2, which means that lambda must be what? 2. Yes? Are you following the logic? Because this is the part that people lose points on, is they do follow some stream of logic, but they don't look at all of it. Like they'll work through this, and they forget that they have to still come back here and look at what happens if lambda is 1. These problems really suck to grade because there's so much work in them that has to be checked. All right, any questions here? Are we at a result right now? We started with x is 0, right? From that, we got that y had to be 1 or negative 1. We were looking at y being 1, and from that, we were able to nail down lambda. So right now, we do have an x, a y, and a lambda, don't we? That's one possibility. So right under this, I'm going to put, therefore, x was 0, right? Y was 1. And then we like to write lambda next to it. So this is x, y, lambda. With me? Do not look at this as an ordered triple, like this is a point on the graph or anything. It's just I'm putting the answers x, y, lambda all in like a set. All right. What do I still need to look at now? See, I just did suppose y was equal to 1, right? I also need to say suppose y is negative 1. That would take care of this one right here. So I'm going to do it right under this. Suppose y was equal to negative 1. I can go back to equation 2 again, right? Equation 2 tells me that, what? Negative 4 must equal lambda times negative 2. Yeah? Is that what it was? Yeah, that's just negative and negative, so. But that just gives me the same lambda, doesn't it? Same lambda? I'm out of room on this page, so I'm just going to keep writing to the side here. This means lambda is 2. Do I have a result then? Do I have an x? Yes. Do I have a y? Yes. Oh, wait, no. Yeah. Whoa, I didn't put negative 1. Why don't y'all tell me that? Negative 1. Sorry, fix that. That was supposed to be y was negative 1 right there. So I had an x, I had a y, and then from that I got a lambda. So this gave me a new point, didn't it? It's not the same point that I had before. It's 0, negative 1, 2. Again, x, y, lambda. That was all based on what happened when x was 0. I got x was 0, gave me two results for y. I looked at both results for y. So I have exhausted the logic, the structure underneath x is 0, right? Now I need to go take a look at what? If lambda is 1. So what happens if lambda is 1? I'm going to do that on another page. Suppose lambda equals 1. Well, I know that if lambda was 1, that was supposed to get me the first equation to be true, right? So the first equation is satisfied if lambda is 1, because that's where it came from. What does lambda being 1 here mean? That 4y must equal 2y, right? 4y must equal 2y. So I'm going to put this here. That implies from equation 2 that 4y must be 2y. And the only way that's true is what? Just move everything to one side. 2y must be 0. The only time that's true is if y is 0, right? So I know what lambda is. Lambda being 1 forces y to be 0. What about x? Where am I going to get that from? Yeah, that's equation 3, okay? So this implies from equation 3, x squared plus y was 0 must be equal to 1, which implies that x must be 1 or negative 1, right? So I've got lambda's 1. That forces y to be 0. That forces x to be 1 or negative 1. So now I have to look at both of those cases. What if x is 1? Suppose x is 1. Is that right? Do I need to suppose? Think about this. Yeah, we have it, don't we? We needed 3 things, lambda, y, and x, right? I have lambda, I have y, and I have 2 possible values for x. So we just have those 2 sets now to put. I don't have to break this down and go different cases because there's nothing else for me to find. I have found everything. Follow? I just had a complete brain fart right there, so I apologize. All right, so what are my points? Again, I'm going to write them as x, y, lambda. 1, 0, 1, and then negative 1, 0, 1 again, right? X, y, lambda. All right. How do you feel about that? Okay, back to this. All of this was based on equation 1 being satisfied, right? From equation 1, we were able to work out all these different possibilities and nail them all down. Now, what about equation 2? Well, you could do the same thing we did over here, right? Let me do that real quick. If I move everything to one side, I get 4y minus lambda 2y equals 0. And then factor out, what, a 2 lambda maybe? 2y? You'll be left with 2 minus lambda equals 0. Do y'all agree? When would that be true? So from equation 2 here, I know that y must be 0 or what? Lambda equals 2, right? But look at this right here, what we got earlier. Isn't lambda 2 here? We already know what happens when lambda is 2, right? And what about y being 0? That's what happened here. And so we got y was 0. But we still have to check it. In other words, I had to go look at equation 2. I can stop now because I've already considered those 2 scenarios, lambda being 2 and y being 0. But it could be that that second equation gives me some other condition I haven't looked at. And so the trouble with these problems is knowing when you've exhausted all the options. That's really where you start to run into it. Does that make sense? How about equation 3? And that's just any point on a circle, right? Any point on a circle. There's infinitely many points that satisfy that. But all the points that we found lie on our circle, right? 0, 1, x and y coordinate. 0, negative 1, they lie on that. So we don't have to consider this third equation. Everything's going to come from these 2. Now, how do we figure out where the max and min is? Well, I need to evaluate our function, our original function, at the points we found. But just the x, y. I don't have to, lambda is only there to have a third variable for the third equation. So I only have to look at the x and y. So I have to do f of, what was it? Was it 1, 0, negative 1, 0, 0, 1, and 0, negative 1. Yeah? Plug that into the original function. The original function. You should get 1 here, also get 1 here. Here you should get 2, and here you should also get 2. So what is the maximum value of that function on that restriction? It's 2. Where does it happen? At 2 different places, right? The minimum value of that function is 1. Where does it happen? At 2 different places. And that kind of goes along with the picture, doesn't it? Two maxes, two mins. Where do they happen? We'll just look at it. Happens right there. You can't really tell. 1, 0, 0, 1, negative 1, 0, 0, negative 1. What do y'all think? Lagrange? This is a different problem. It looks the same, but it's a little different. Find the maximum and minimum value of this function on this disk. So the main difference here is that your restriction is not a curve, right? It's not an equation, it's an inequality instead of an equation. So this is like a closed bounded set. Do you agree x squared plus y squared less than or equal to 1 means your domain is everything on the ground there inside that disk and the edges? Yes? So the way that we approach this is pretty nice. What we do is we break it into two separate problems, just like we did before. We do around the edge. How do we go around the edge? How do we look at just the edge? Lagrange, right? Then how do we look at what's inside? What we had earlier when we were doing the capital D, although we don't have to find capital D, we just have to find the critical points, which was where the partials were equal to 0, and then we could set them equal to each other or just solve them. So it's going to be basically a reproduction of Lagrange, what we just did, which found 4 points, didn't it? But now we have to look inside. So there's not a whole lot of work that I'm going to be able to show you for this other than the inside part, all right? So for example 2, I do Lagrange for the outer edge. In other words, I do Lagrange on this equation. And that's one set of work. Check. We've done that already, right? The next part is inside. So be looking at x squared plus y squared less than 1. So on the inside, all I need to do is take the partials, set them equal to 0, find critical points. So what is the partial of f with respect to x? We said it was what, 2x? What's the partial of f with respect to y? Is it 4y? Set these equal to 0. You get x is 0, right? Set the partial with respect to y equals 0. You get y is 0. You should have done that on your homework, right? So I do have a critical point. The critical point is 0, 0, right? That's my critical point. Now plug that into the function to find its value there. What's f of 0, 0? 0, right? Now what we're doing, we're done at this point. All we have to do is go back, look at what we did with Lagrange, right? Our max was 2 and our min was 1, but that's when we were on the edge. Now we're allowed to look inside. When we look inside at 0, 0, which is in our domain, right? That is in our domain. The function's value is 0. So the lowest value is no longer 1, the lowest value is 0, and it happens at the origin. And that you can tell, there's my domain. Here's the domain plugged in. Notice the difference between that blue curve we had before, right? And now we have this, it's not just the edge, that blue curve up here, it's everything inside also, right? All those points inside. So the lowest point here, we have those two high points, but now our lowest point is that point down here on the bottom. See the difference? So if there's a way that we can come up with the constraint equation to go around that edge, we can use Lagrange. Pardon? You want me to go back to the work? Go ahead. let's do this one. This will probably work pretty quick. F of xy equals 4x plus 6y. This is a plane, right? That's a plane. So there's our plane. We are restricting our plane to a what? Circle. So there's my domain on the ground. If I plug those points in, just those points into the surface, and I pull that surface out, I get that, right? I'm trying to find the highest and lowest points, which should be those two right there. Yes? Again, take a step back. Can you imagine doing this without the visual part of it? I mean, you would be able to do the math, right? I mean, the math isn't that crazy. But knowing what you're doing is kind of a big bonus, isn't it? I always think it is. Like visually what you're doing. All right, here we go. Sometimes the problem looks pretty, harmless, and then it turns out to be a disaster. But this one actually looks harmless. I think it's going to be harmless. Mostly because those partials are pretty clean, aren't they? I have a function of two variables. I have a single constraint, right? Function of two variables, single constraint. Because where we're headed is function of three variables, single constraint, function of three variables, two constraints. I mean, you can have as many variables and as many constraints as you possibly need to have. So let's try and get some of this language down. Function of two variables, single constraint. All right, I'm going to have three equations. Equation 1, equation 2, equation 3. First equation is the partial of f with respect to x. Very nice. It's 4 equals lambda partial of g with respect to y. Now remember the g one is this one, right? Partial of that with respect to y is 2y. Second equation should be what? Just give me what it is. 6 equals... Oh, wait a minute. What did I do? Yeah, it is. Change that to an x. Right there, x, 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 x. Yeah, that's probably confusing you there. Everyone got that? Okay. That one over there, 2y. Last equation is your constraint. I'm going to divide 2 on both sides for this one, equation 1, and over here. Okay. Any ideas? Solve for x and, did you say x and lambda or x or lambda? So you just isolate x by itself here? Is that? If you pull the 2 over, you won't be able to factor anything out like we had before, right? And set each one equal to 0. That's what makes this problem a little bit different than the one before. I can't set both of these equal to 2, right? That's a big no-no, right? Can't do that. You can only do that if that's 0, right? Okay. Okay. And do what with equation 3? Solve for one of them, and then do what with that? Plug it into one of those. So if I solve this one, if I solve this for y, and then come in and plug it in here, I'll have lambda and x. So I'll still have 2 variables, won't I? Yeah, I don't know, maybe. I don't know, so we could sit here and look at it and think about it, but let me just show you, right? And that way you've seen, right? You've seen one approach, a different, a way you can attack it. But again, being very careful with the way we keep track of everything, all right? The keeping track of everything is the thing that takes time. All right, I'm going to start with equation 1. 2 equals lambda x. I'm going to choose to solve this for x. So the only way to solve for x is divide both sides by lambda, right? So I'm going to divide both sides by lambda. So to do this, watch what I do. Suppose lambda is not 0, right? I have to make that assumption first. If lambda is not 0, then that implies that x is equal to 2 over lambda. If I forget that, I mentioned this earlier in this class specifically because I knew we were going to hit Lagrange one day. If I do not consider this, right, if I don't do this, then later on I'm going to forget that I need to come back and say, well, what if lambda is 0, right? So I'm saying lambda is not 0. I'm allowed then to divide both sides by lambda and get this, right? Also, equation 2 would imply what? Again, lambda is not 0. What could I say from equation 2? That y is equal to what? Y is equal to 3 over lambda. Now I know what x is in terms of lambda. I know what y is in terms of lambda. And so I should be able to go to equation 3, replace x with 2 over lambda, replace y with 3 over lambda, and I will have an equation with just lambda in it. So I should be able to solve it, right? So now going to equation 3, which tells me that x squared plus y squared must be 13, I get 2 over lambda squared plus 3 over lambda squared must be 13. And now let's square and have fun. All right. Squaring 2 over lambda gives me 4 over lambda squared, then 9 over lambda squared equals 13. I can put those two together, can't I? Same denominator. Hey, what is that? 13 over lambda squared equals 13, which means lambda squared has to be 1, right? Moving things around, or negative 1. Well, I said lambda squared has to be 1, right? Lambda squared has to be 1, then that means lambda has to be 1 or negative 1. So that means that lambda squared has to be 1, which means that lambda has to be 1 or negative 1. Which is a good thing to conclude, right? Because I said lambda can't be 0, and at the end I'm saying lambda is 1 or negative 1. If I would have said all this, and at the end it said lambda has to be 0, I've got trouble, right? First I say lambda can't be 0, and at the end you get lambda 0. That's called a contradiction. So somewhere in there you've shown that can't happen. All right. So remember, we're looking for 3 things, right? X, y, lambda. All I've gained from all of this work so far is what? What lambda can be. And there's 2 possibilities. So I'm going to come here, slightly indented, suppose lambda is 1. So I'm still working within all this framework here. Suppose lambda is 1. If lambda is 1, what does equation 1 give us? Well, we had already done this up here, right? Here was equation 1. We suppose lambda wasn't 0, and we actually have equations for both x and y, don't we? So I can tell you that x is going to be 2 over lambda, so that's 2 over 1, which is 2. Since x equals 2 over lambda, that means x is equal to 2. And then similarly, equation 2 gives us that y must be 3 over lambda, which means that y must be what? 3? Yes? So do we have x, y, and lambda now? Yes? If lambda was 1, that meant that x had to be 2 and y had to be 3. So we have one solution right here. I'm going to put it to the side here. We have x is 2, y is 3, lambda was 1. Now what do I need to suppose? Lambda is negative 1. I'll do that on the next page because I'm out of room. Still going to stick with the indent. Suppose lambda is negative 1. Then equation 1 tells me that x must be 2 over lambda, which means that x must be negative 2. And similarly, equation 2 tells me y must be negative 3, which gives me another point, negative 2, negative 3. Lambda is negative 1. Questions? We done? Back to the, yeah, that was all part of this thought. That was all part of this original assumption that lambda was not 0. Yes? That's right, but I have to consider it, right? Yeah, that's exactly the conclusion we're going to draw right now. So whenever we said lambda wasn't 0, I wasn't even thinking about if it was. Now I am. And it's going to come up to be something ridiculous that doesn't make sense. So here we go. Going back to that next page. Now, suppose lambda is 0. Then equation 1, in its most simplified form, but without dividing through, right? Just right here, if lambda is 0, equation 1 says 2 equals 0. Huh, no way, right? It's not happening. Therefore, lambda cannot be equal to 0. Are we done? Well, what if I had started with the equation 2 instead of equation 1? I could have supposed that lambda wasn't 0, right? Divided through. Then I could have got to this, but then I would have got to this, and I would have been in the same place, wouldn't I have? Now, I solved for lambda in both of these problems. Could I have solved for no, wait, hold on. I didn't solve for lambda. I solved for x and y. Could I have solved for lambda in both of those problems? Could I have? If I would have solved this for lambda, then I would have got what? 2 over x, and I would have had to have said, suppose x is not 0, then lambda is 2 over x, right? And then over here, I would have had to have said, suppose y is not 0, and then divide, and I'd say lambda is 3 over y. So then I'd have lambda is 2 over x and 3 over y. So couldn't I set those equal to each other? So I'd have 2 over x equals 3 over y, which would give us an equation with 2 variables. I could solve for one variable and stick it into this equation and solve for the other. So it would have worked, but it would have been a different logic, a different set of logic here. Probably a little longer, but you would have gotten there. That's it. We're done. And those 2 points, we need to check them, right? I need to figure out what f of, what is it? F of 2, 3, and f of, was it negative 2, negative 3? I forgot what the function was. So 2, 8, 3, 18, what is that? Is that 26? And negative 26? You get the same thing? You understand what I'm doing there? Plugging that into the original function. Oops, I went too far. Right here, 2, 3, negative 2, negative 3. I believe that matches up with our picture. So do you think you want this on the test or not? Maybe I should show you a few more, like this one. Find the maximum and minimum of the function e to the x, y, with the constraint x cubed plus y cubed equals 16. Now we're getting there. I won't show you the picture yet of what this looks like. So I'm going to have 3 equations. What's my first equation? Y e to the xy equals lambda times 3x squared. Next one, x e to the xy equals lambda times 3y squared. And then, of course, my last is x cubed plus y cubed equals 16. That's almost dizzying to look at, isn't it? So I'm going to show you a trick, not a trick, shortcut. This one has y e to the xy. This one has x e to the xy, right? They're almost the same, almost. Except this one's y and that one's x. So watch what I'm about to do. Right now I'm not supposing, well, I guess I do have to suppose something right now. But you won't see why until after I do it. So suppose x and y are both not 0. Well, could they be? Let's just look ahead. When we do look at this case where they both are 0, it's not going to satisfy the last equation, right? But I need to be clear right now that they're not 0. The comma means and. So suppose x and y are not 0, both 0. Then my equation 1 is equal to xy e to the xy equals 3 lambda x cubed. So what happened there? I multiplied both sides by x. Now, the only way I could do that, the only way I can multiply both sides of an equation by something is if I promise you it's not 0, which is why I had to say x can't be 0. So as long as x is not 0, I can multiply both sides of the equation by x. Now, if I go to equation 2, I can multiply both sides of equation 2 by what? Y. Because if I do that, what appears on the left side now is the same, right? If these two are the same, what can I do with these two equations? Set them equal to each other. Do y'all follow that? It's tricky, but it works, okay? Equation 1 being set equal to equation 2 would mean that 3 lambda x squared, or x cubed, plus, or no, equals 3 lambda y cubed. And how are you going to solve this? Or figure out what's going on here? Can I get rid of the 3's? That I can do, right? Can I cancel the lambdas? No, not unless you promise me lambda's not 0, and I don't feel like going there. So instead, why don't we bring everything to one side? Lambda x cubed minus lambda y cubed must be 0. What can I factor out of the left here? Lambda. Set lambda to 0. So you get lambda equals 0, or what? X cubed minus y cubed equals 0, which means that x cubed equals y cubed, which means that x must cube root both sides. X must equal y. Right? I set this right here equal to 0 and got this. Then here. So let's back it up. What happened? What the hell happened here? I suppose that x and y were both not 0. From that, I'm able to conclude that lambda must be 0 or x must be y. So let's go take a look at each of those scenarios. Suppose lambda is 0. That's my first thing I'm going to look at. What if lambda was 0? Yeah, the first equation, that whole side would be 0, wouldn't it? Which would mean y e to the xy would have to be 0. E to the xy is never 0, which would force y to be 0. So lambda being 0 implies that y must be 0. This implies that y must be 0, which is, what's that symbol? Y'all know what this is? Oops. Y'all have seen the arrow, right? Like this? That means like, you know, if x is 2, then x squared is 4, right? This is like an implication almost. That means that's true. Well, when you draw this symbol, the symbol I have up there, it's actually an arrow with an arrow going the other way. And so what it represents is a contradiction. Okay? It's a contradiction. We just contradicted ourselves. What we did is we said, hey, y is not 0. And at the end we got y is 0, which means that we can't let lambda be 0 because it forces a contradiction. So we can chunk this out. It's gone. I don't have to look at lambda 0. But I still need to look at what? If x is y. So I'm done with this. So now I'm going to do it to the side. Is that all right if I do it over here? Normally I would just keep moving down with my paper here, but because of wanting to keep it all on one page. Suppose x is y. What can I do with x being y? Go to the third equation and replace x with y or y with x. It doesn't matter. Equation 3 tells me that I will have x cubed, replacing the y with x, plus x cubed must equal 16. That's 2x cubed must be 16. So x must be 2, right? But if x is 2, what's y? 2. Because we said x had to be y. Do we have an x, and y, and a lambda? Well, we have an x and y, right? This is gone. We're not even dealing with that. Coming back up, did we ever say what lambda was? No, right? But could you tell me what lambda is if you know what x and y is? Yeah, you could get it from where? Either of these, right? Now, I'll give you my opinion on things. If you find the x and y, but haven't found the lambda, you don't really need the lambda. You don't need to find it, because all you need is the x and y to plug into the function, right? So you can kind of stop at this point. It's not that important. But a lot of times, we need the lambda to get the x and y. This just happened to work out where we didn't need it. All right. So let me come back up here, and next to this, I'm just going to say, suppose x and y equals 0. Equation 3 would give us 0 equals 16, which is a contradiction. 0 is not 16. Now this is kind of something to ponder for a second. In the beginning I said, suppose x and y are both not 0. I need to look at the other case. Is the other case that both x and y are 0? Or is there something else I still need to look at? What if just one is 0? See, because this said, suppose they're both not 0. This says, suppose they both are. But what about just one? Right? Just one. So what would happen if I suppose that just one is 0, just one of them is 0? Suppose x equals 0 and y is not 0. Where can you come up with a contradiction here? First equation? Yeah, because this side's going to be 0 again, right? And then you're going to have e to the 0. E to the 0 is 1, so you have y equals 0. But wait a minute, didn't we just say suppose x is 0 and y is not 0, and we come up with y is 0? Again, a contradiction. So I'm not going to show that, but that's not going to happen. Then you do it the other way around, equation 2 would give you the same thing. So we're pretty much there. We have our, what? Is that it? We just have a single answer? Uh-oh. Uh-oh. F of 2, 2. What would happen if we plug 2, 2 into that function? Don't we get e to the 2 times 2, which is e to the 4th? What is it? What, is that a max? Is it a min? What is it? How do we know it's a max? How do we know that's not the lowest point? So let me give you the picture, and I'll try and help motivate what we're going to do now. Here's e to the xy. Okay? That's e to the xy right there. That's what it looks like. We are restricting it to this curve, and this is the curve x squared plus x cubed plus y cubed equals 16 down on the ground, right, looking from the top. So I'm going to go slap that in over here. There's the domain. See it right here on the ground? When I plug that into the curve, it's hard to see, so let me pull the curve out. See it right there? It's a max. However, how do I know that? Go ahead. I agree. It can't be negative, but you could have positive. Like imagine that went. I'll just give you an example of a function that dips down. That's never negative, right? There's only one way we can do it. Well, maybe there's more than one way, but there's an easy way. We go back to something that you don't really think about too much. We know this is either a max or a min, right? It's one or the other. So a good way to know if it's the max or min is find some other point on that curve and compare it. If this is the max, e to the fourth, then any other point on that curve, if I plug it in, should be smaller than e to the fourth. If I plug something in, I get something bigger than e to the fourth, then it's got to be the min. But the question is, where am I going to get a point on this curve? It can't be any point on the entire surface. It has to be on this black curve. So give me something that lies on this blue curve, an x and a y coordinate that lies on this blue curve that I can test. So what's an easy solution to our constraint equation? Here's our constraint equation. How about 0? Oh, this isn't the right one? Oops. Oh, here we go. How about, I'll stick with 0, but not 0, 0. How about 0 cube root of 16? It would work, wouldn't it? Yes? Okay, that lies on it, right? Okay, so come in here and plug in e to the 0 times cube root of 16, but 0 times cube root of 16 is 0, e to the 0 is 1. We had e to the fourth, didn't we? It's a max. Does that make sense? That's the cleanest way to do it. Bigger than it. That's right. So we're here, we're like max or min? Well, I don't know. Max or min, I don't know. Let's test a point. Let's test 0 cube root, what was it, 16? F of 0 cube root of 16 gave us e to the 1, or no, e to the 0, which was 1, which is smaller than e to the fourth, which means that it was a max. That's a max. Therefore, the point 2 to e to the fourth is a max. All the problems that I've chosen to show you all have little subtle differences in the algebra required to figure out what these points are. You know, on one of them, what the first example we did, right? We moved everything over to one side, factored, set equal to 0, and worked through it. The next one, we couldn't do that, so we had to solve for x and y and restrict ourselves a little bit. On the one we just did, we had to be very clever and come in and multiply both sides by something to get equation 1 and 2 to match each other so we could set them equal to each other. These are all different approaches, right? I think that's what makes part of the Lagrange difficult, is that there is no like cookie cutter, like it's not like taking a partial derivative where it's just a rule that you're following. You have to be kind of clever but careful with your algebra in this. Got 20 minutes. We've done pretty good. I want to do this one more example in the next 20 minutes, and we will be about halfway through Lagrange. We haven't started function of three variables with a constraint. Imagine what's going to happen, though. If you have three variables now and a constraint, you're going to have x, y, z, and lambda. 4 equations now. So that becomes a lot more challenging. And the thing is, I always have Cal 3 students who are like, well, if we have a system of equations, 4 equations, 4 unknowns, why don't we just use linear algebra, just use like a matrix or something? Well, why can't we? Why can't you just use a matrix? Because matrices are used to solve linear systems of linear equations, right? Systems of what equations? Linear. These aren't linear equations. These are nonlinear equations. There is no method, just out-of-the-box method to solve a system of nonlinear equations. So if they were linear, yeah, it'd be all gung-ho, let's go, Gaussian elimination, let's use a matrix, something like that, but we don't have it. So we're screwed. So it all comes down to the algebra, how good we are with algebra. All right, next example, 1 over x plus 1 over y. Now, I'm trying to adjust to this new schedule after picking up that class. I'm like, we've got 20 more minutes. I'm all excited, and I realize I have another hour, 40-minute lecture after this. It'll be my 3rd one today. Man. I sound like a big wimp, don't I? People working 8-hour days out in the sun digging ditches, and I'm sitting here complaining about talking about math for a couple hours all day. That should be fun, right? We won't even look at the picture. Let's just get right to it. Partial with respect to x. Negative 1 over x squared. You agree? Equals lambda times, what's the partial with respect to x for g? That's right, negative 2x to negative 3, which I'm just going to drop down like this. I believe that my second equation is going to be the exact same thing, but with y's, right? And then my last equation is over here. It's all happy. Well, recommendations, suggestions? Anyone see anything we can do here? Multiplying by the largest one, like x cubed on both sides? Is that what you're saying? Yeah, okay, so either way, I think we're all get to the same place. My only concern would be, can I do that? As long as x isn't 0. And is it even possible here? It's not in the domain of the original function, right? I mean, you can't plug 0 even into the original function. So we can automatically throw out the possibility of x and y being 0. We don't even have to consider it, right? But I'm still going to be meticulous. I'm going to say suppose x and y aren't 0. Then equation 1 becomes multiplying both sides by x cubed and -1, because I want to get rid of these negatives. However you want to get rid of the negatives, you do it. It should turn into x equals 2 lambda. Yeah? Equation 2 should turn into y equals 2 lambda. Oh man, this one cannot be this simple. Because if x is 2 lambda and y is 2 lambda, then that means x is y, right? That implies x is y. If x is equal to y, then I can come to the third equation and replace my y with x and solve it for x. This is going to work out nice. So from equation 3, I have that 1 over x squared plus 1 over x squared must equal 1, which means 2 over x squared must equal 1, which means that x must be plus or minus what? Square root of 2. But that means that y must be what? Well, maybe we should take these case by case so we don't screw up the signs. Suppose x is equal to the square root of 2. Then what's y? Remember, x was y, right? So y must be square root of 2. Suppose that x is equal to negative root 2, then we get y must be negative root 2 also. Do we have lambdas for each of these? I should have got them, but see, I already have a habit of if I don't need lambda, I'm not going to go get it. But could I have gotten lambda from this right here? Yeah, right here, because right here, this is x is 2 lambda, so if I want to know what lambda is, I just divide x by 2. So lambda, if I want to put it here, lambda would be root 2 over 2. And over here on this one, lambda would be negative root 2 over 2. Did I lose anyone on this? So we have 2 points here. Anything else to consider? What if x and y were 0? Well, we already said it's not in the domain. It's not going to happen. So I'm not even going to look at it, but I think we're good. So now I need to look at what is f of root 2, what's f of negative root 2, negative root 2. So you get 1 over root 2 plus 1 over root 2, which is 2 over root 2, which you could leave like that, or you could rationalize. That's just root 2, right? Multiply top and bottom by root 2. 2's will cancel. Get root 2 up there. Same thing here. Max and min. Max and min. Take a look at it. Here's the restriction in two-dimensional space. Notice the restriction is not a function, like a function of x and y. It's a curve, right? Fails the vertical line test, but it is a restriction. Here's our surface. The surface is looking pretty cool, huh? It's pretty cool. And we found a max and min. Man, I don't see it on here. Where is it? Huh, it's hard to see it. Well, here's the domain on the ground. Here's plugging that blue stuff into the curve, or into the surface, and I'll pull the surface out. So it's that black curve, right? That's it right there. Pull the domain out. So on this black curve, we have a highest and lowest point somewhere. And we found them, and there they are. See them? Okay. It's good stuff, right? No. Now I don't think we're gonna get into this right now. What I wanted to show you is that I was kind of tired of doing Lagrange problems because they were so tedious. So I just wrote some code in Mathematica to do it. So like on the problem we just had, it was like, well, the original function was 1 over x plus 1 over y, right? The constraint was 1 over x squared plus 1 over y squared. And it was equal to what? What was our constraint equal to? 1? No, I didn't run this before I came into class, so I hope this friggin' works. There it is, yeah. X, y, lambda, x, y, lambda. That was a little faster. And it actually plugs it in to the function and tells you what the value is there. So that's the min, and that's the max on that restricted curve. And as we move on, remember I said we have function 2 variables, 1 constraint. I have code here for 3 variables, 1 constraint, and then 3 variables, 2 constraints, which we haven't looked at yet. That's probably why the PDF file didn't open. It may not have known what to do with this when it tried to save it. I don't know. I haven't figured it out. Okay. Trying to think of a good problem. Well, let me set it up, and then we won't actually do it. I want you to go back and look at. We talked about. Man, where is it? It was the one. Maybe someone can help me here. Look in their notes. It was the problem with. Oh yeah, there it is. There it is. That wasn't so hard to find. It was this one. We had an ellipsoid, and we wanted to construct a rectangular box inside of it, right? And what we had was a volume equation, right? We had this volume. We knew the volume was 8xyz. Do y'all remember this picture that I had with the different octants? And we said what sucks, though, is that we don't know how to find the max and mins of something like this because it has 3 variables. Everything that we have developed, we needed to look at it as v of xy. Yes? Where we're headed, though, is that we will not have to take it to this because we will have a volume as a function of 3 variables, right? And our constraint is that you must live on an ellipsoid, which means our constraint equation is here, and our f function is that. Does that make sense? So we will be able to solve this problem without the headache of what we had to do here. Remember that? Junk, 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 all that junk, junk. And then we got over here, and it was like more junk. And everyone was happy, and at the very end, we got an answer, right? Lagrange is going to let us do that. In fact, help me remember this. I need to help. You need, please remember what this is, right? 936, 436. Got it? Okay. Let's see. That is a function of 3 variables. So the function I'm trying to optimize is 8 times x times y times z, right? That was our, okay. And our constraint was 9x squared plus what? 36y squared plus what? 4. Tell you, man, my brain just doesn't work that way. And then that equal to 36. I'm hoping I don't look like a complete ass here when I hit this button. I really have not run these in a long time. Yeah, that was the answer. I remember that. But not only did this one look in the, we restricted ourselves into the first octet. Remember that? We said x and y and z were all greater than, or yeah, x, y, z were all positive. This Lagrange doesn't even know that, doesn't even care. But the one we got was, where is it? Where are they? I should have 2. Negative, negative. Is there more? It's just getting cut off. Yeah, this is it, but yeah, it is. It's just 2 What I'm trying to get is my x, y to both be positive. None of these carry. I should have both x, y positive, x, z. Something seems amiss here. I think it's cutting off. I think I told, when I wrote the code, I think I said, like, only get the first so many solutions. Because it's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I probably told it, like, don't only find the first so many solutions. I'd have to look at the code, which I'm sure is not something you want to do. I don't see it. I don't see where I... Okay, it doesn't matter. Sorry, I'm keeping you here. You don't need to be here. Let's talk about the test. What do you all think? Do you think that you would want this stuff on it and wait till Wednesday? Or do you want to just do it on Monday? Talk to me. What do you feel like? We have an hour, 40 minutes to take a test over everything we've talked about. It's a lot. I have no idea, man. I haven't made the test. Okay, so how many of you want to wait till Wednesday? Well, we have to look at the 3 variables and a constraint, and then 3 variables and 2 constraints. What's that? Yeah, the Lagrange wouldn't be there. See, Lagrange is hard to test on because one Lagrange problem could theoretically take you 30 minutes, We did how many today? 4? Did we do 4 or 5? 4 or 5 took us the entire class. Yeah. The what? Yeah. Yeah. No, it'll be in line with this. Well, it'll be in line with this. No. I've already told you that the testing class is more like what the problems in the book are going to be like, and more like what I demonstrated in class. That's what it's more, because I can't give you the harder problems are the ones I send you home with. Those are the ones that I expect to take a little more time, and that's why I do that. It's kind of a give and a take. I can't give 4 tests in this class. We won't finish the book. So I have to give 2. That's the only way I can ever finish the book in this class, if I give 2 tests. But the sacrifice for that is that those 2 tests are worth a lot, and it can come from a lot of different material. So I have to pick, and I'll probably pick what you don't study, right? That's exactly what's going to happen. I'm going to pick the stuff you don't study. Yeah, because I think I said I would do that. I said we could do the test on Monday, and I'd throw in Lagrange as a bonus. So let's take a vote. Okay? Monday, keep it as is. Okay? All right, so it's not an overwhelming majority to change it. So we will keep it as Monday. If everyone wanted to go to Wednesday, if it was a big, majority, let's go to Wednesday, we would do that. All right? So what have I said to look at? Everything, yeah. But focusing on, the notes, looking at the examples we went through in class, going into the homework, finding problems in the homework that match the things we did in class, looking in the chapter reviews for problems that look like the homework problems and the in-class problems. Stay away from the take-home stuff. Don't be trying to go and do all that. All right. Well, be ready. Come fed, come rested, and do your best. I think you'll be all right. Have a good day. Have a good weekend.